So I see you finished the lecture.
Yeah.
I just need to stare at it.
So it's mostly review of topics that we mentioned last time, and I will be going over these again. So if you want to take a look, you can take a look. If you don't want to take a look, then you can just wait.
Really short. All right, so we are done with the syntactic era, and now we are entering the semantic era of continuous combinatorics.
Well, not quite. I will finish the syntactic part first, because last time we talked about the objective was to get to the semi-definite method, and we didn't actually get there. I didn't get to state. It's a term that has quite a complicated statement, but nevertheless, it provides a very useful family of semi-definite programs to provide the upper bounds for extremal combinatorics problems. So the plan today is actually to finish this part of Lie algebras in the first part of the talk. I'll probably take a break then. And then we'll talk about the second part, which is semantic limits. So it's the right side of the triangle, but maybe I'll talk a little bit about exchangeable arrays, which is also a little bit towards the left side, because it ties very nicely together with this theons, which are the semantic limit version of this. So just a brief review of last time. We talked about these, we were dealing with these general combinatorial objects, which were encoded by as models of some fixed universal theory. Remember, universal theory was you had some axioms, but they all used universal quantifiers. And the reason why this, what?
Axiom and?
They all use universal quantifiers. So you only use for all, right? And the reason why this is important is because every time you restrict a model or a combinatorial object to a sub-object, it's still a model or a combinatorial object of the family. And that allows you to define densities. Now you have these things called flags, which was you have this combinatorial object, and some part is special, it's labeled, and it's an embedding of a sigma model, right? There's some sigma, which is a fixed model called the type. Now you can talk about densities of flags inside one another, where you require labels to be preserved. And convergence was requiring that densities were convergent in your sequence. Every time I give you some small model or some small flag, and I have a sequence of flags, the density of this, if I compute it on the sequence, needs to be a convergent sequence of numbers for any finite flag. And then we asked, well, what are the limits of these? If I take,
sorry, did we show that this thing always converge?
no, it does not necessarily always converge. There are sequences that don't converge.
But is it converging up to subsequence?
Yes, it was a compact space.
It's a compact space?
Yes, it's a compact space because after all, you can think that each of the densities is a number between 0 and 1, and there's only countably many finite flags or finite models, up to isomorphism, of course, right? Because the language is required to be finite. So at each finite size, there's only finitely many, but you take all finite sizes, so it's countably many. So it's compact, right? Compact metrizable, all nice properties of topology. And then we asked the question, well, if I just define phi of some f to be the value of the limit of f, what kinds of phis, what kinds of these functions or elements of this cube with countably many coordinates can arise as limits? And it turns out that the answer was you can define these flag algebra, which is some quotient of formal linear combinations of flags. If you need a reminder what these things are, it's on the right board. And by the way, Zoom audience, anything that's on the sideboards can be found on this website. But nevertheless, we define this R algebra. It turns out that the limits were exactly the set of positive homomorphisms from this flag algebra to real numbers. And positive means densities of flags were non-negative, right? So that was what we saw last time. And the whole reason why we wanted to do this is because we were interested in generalizing this proof of Manto's theorem, the semi-definite proof, to arbitrary extremal combinatorics problems. So just a reminder how this proof went. We had the edge, and then we added some average of some square, which is certainly non-negative. Then we rearrange this computation, and we could get this expression of densities of three graphs of size 3. And then we observed, okay, there's a 1/6, it's almost 1/2, but this has no negative density. You can complete it, make it 1/2 this. But for a triangle-free graph, this is all possible models of size 3, or all possible 3 graphs in a triangle-free graph. So these densities add up to 1, or it's the 1 of the algebra if you want. So this is exactly equal to 1/2. So what we proved is that the edge density is at most 1/2. Or more formally, in the flag algebra, you could define the semantic cone, which was the elements of all the flag algebra, such that doesn't matter which limit you look, the element is non-negative. So this is actually not an inequality of densities, but rather an inequality that takes place at this level of semantic cone, if you want to be more formal about it.
Can you repeat again, what's this semantic?
Semantic cone is all elements of the algebra such that if I give you any limit, phi and hom plus, phi of that element is non-negative, right? So this defines an order by saying f is greater or equal than g if and only if there are differences in the semantic cone. And you can also see this proof as saying 1/2 minus h is always greater or equal than 0, right? Always in the semantic cone, right? Oh, for triangle-free graphs, of course, right?
So you want just non-negative coefficients in your expression, and because of that, you don't say something greater than 0, a polynomial is greater than 0. You just separate its positive and negative parts to the two sides.
So this is the analog of positive semi-definite matrices.
Not exactly, because these are all non-negative elements. In particular, squares and sums of squares, etc., are in this cone, but not everything in this cone is necessarily a square of sum of squares.
Okay.
Yes.
I meant the analog.
Yeah, but there's no positive stuff.
In the usual way of defining semi-definite ordering of matrices.
Yeah, exactly.
You don't say, you say one is greater than other.
Yes.
The difference is semi-definite. Yeah, in the same way. Yeah.
More generally, every time you have.
It's like the way this is the main tool that you have to prove inequalities.
Yes, but more generally, every time you have an algebra and you have some cone inside it, it gives you an order by defining it like this. So these gives you positive elements with respect to this cone. And this cone makes a lot of sense because it's the cone of things that you really want to see being non-negative, right? These are the densities that are non-negative, or polynomial functions that are non-negative in every possible limit. Okay, so that was any more questions before we proceed? It's still a review, so it's fine even if it's something we already seen. Now, if we look at this proof again, there are some small technicalities that we needed to handle, which is, of course, squares should be non-negative, right? Because these are algebra homomorphisms. So if I have a square inside, it goes outside, and now it's a square of some real number, which is necessarily non-negative. But we have this averaging operator, which we didn't get quite to what it was. And if the square is negative after I apply the averaging operator, somehow I need to prove that this is still non-negative, right? So this I did not prove, and we are going to prove today. And these are these two topics, which I just mentioned last time, but we didn't really get to work with them. So averaging operator, that is the brackets that's appearing there. So it's some linear map that maps from the sigma, the flag algebra corresponding to type sigma, to the flag algebra corresponding to no types. And it's linear, so it's enough to define on all flags. And the definition is, well, you erase the labels, so the underlying model of the flag, and you multiply by a number, and this number is, you pick uniformly at random an injection and see what's the probability that this partial labeling that you did gives something isomorphic to F, right? Perhaps what?
To F or to sigma?
To F, because, so I'll give you an example, right? So for example, if I have, say, this model.
So it's the probability,
So what the underlying model is going to be this, right? And what's the probability that if I label one vertex uniformly at random, I see a picture that is isomorphic to this? This is 1/3, right?
Sorry, I didn't see. So what's written, the coefficient is G sigma of S.
Yeah, Q sigma, maybe.
The sigma was not.
There's a tiny sigma.
Would you mind doing this example slowly and
yes,
explaining
so
what's the explaining what is sigma and what is.
Sigma is the type one. So this is a notation for the type which has only one vertex and the vertex is labeled. So this is the type one. Right? The type is a completely labeled model, if you want. Right? A sigma flag is a partially labeled model such that the labeling gives you something that looks like that type sigma. Right? So this is a one flag because if you look at the partial labeling, it looks like one vertex that is labeled, right? It's important to do this because sometimes you have weirder things, like for example, this is a different type of flag than this type of flag because what happens in the labels is very different, right? But nevertheless, this is a one flag, so we can apply this averaging operator going from the one flag algebra to the zero flag algebra. And what does it do? Well, you take the flag, you ignore the labeling. So put the model here. And there's a coefficient in front, which is this Q sigma, which is the probability of if I label uniformly at random a vertex, when do I see something that's isomorphic to this, right? So there's only three possible labelings. I can label this, I can label this, I can label this, but only labeling here, I see something isomorphic to that. Notice that, for instance, if you do something slightly different, say, if I was looking at this flag, this one flag instead, where the label is here, now it's 2/3, right? Because labeling that vertex as well does give something isomorphic to this.
But if you add one on the bottom left and two on the top, the random labeling has to be such that you have an edge between the two, or
It should be 2/3 for the.
It will be, you're gonna get, you need, it's 2/3.
not just uniform labeling, right? Like the 1, 2 has to capture an edge.
You first pick one, it needs to be 2/3, but then you pick this out of the two remaining vertices and it needs to be on the top. Right, so it's one.
Wait. No, you pick it out of, you need to pick it like a vertex that's neighboring that.
Yeah, so first pick one. If you're going to pick the label one, it needs to be one of these two guys. That's probability 2/3.
Yes.
But then you need to pick two and it needs to be the top vertex, which is 1/2.
Okay, random. You don't condition. You just want to find what you're looking for.
But
Okay. Any more questions? Do we need another example to make this clear?
Why did you write the E on the?
Oh, because that is another different type. Now, E is this type that has an edge and two labels, right? So the type of this guy is the one type, and the type of this guy is the E type. It's a different type completely. It's just the standard notation for these. Okay.
Wait, so why does this matter? What is the difference between, let's say, the type E and the type of like non-edge? Is there any difference?
Yes, yeah. This is what we call the E bar. It's the non-edge type.
Yeah, but like in the way we.
Well, this doesn't make sense to apply the E bar operation here because the E operation is for E flags. The E bar operation is for E bar flags. You cannot apply the E operation. The operation goes from the E flag to.
But if you had one on the left, bottom left, and two on the bottom right, it wouldn't be 1/3. It would be 1.
Okay, now let's
Just
do
so
the
that everyone is in line with that.
E bar averaging operator. Then what you're gonna get is let's see, is
There's only
2/3, 1/3.
Half, I want. 5/3 and not half.
You don't want to get the middle one.
Wait, so now I don't follow.
Pick the one, needs 2/3 of the chances you land here, and now the two, also you need 1/2 of the chances to land on the other one in the plot.
Yeah, I thought you condition on.
No, you don't.
No, you don't. You pick uniformly at random an injection and.
So for the.
But I'm picking it in steps, right? I'm picking it in steps to make it easy.
So for the
Am I
average.
doing it
I
slowly?
thought it was conditioned
No,
on the.
no, that's how we.
Let's wait for people to stop. Okay, so you pick uniformly at random a partial labeling, right? But I'm picking it in steps to make it easy, right? So let's first pick the label one, right? It needs to go in one of these two vertices, right? What's the probability that happens is 2/3. Condition on that, what's the probability that when I pick the label 2, it also lands on the other of the 2 birds, right? Because that's the only way it's going to get something as well to this. So it's 1/2. So 2/3 times 1/2, 1/3. Right?
Let me still ask again. So for the averaging operator, does it matter if I'm averaging over? Why does it matter if I average over E or E bar? Like what I'm computing is
No.
the same thing.
It's not the same thing because the sigma averaging operator, the input is a sigma flag. Okay, so the part that's already labeled needs to span something that looks like sigma.
Okay, but for the computation of this,
For this is a coincidence that these guys gave the same. But
no, I'm not talking about I don't care about the third being the same. I care about the fact that what I'm computing is not conditioned on anything about the structure of like E or E bar. It's conditioned only on.
I think I can answer your question. So in the bottom one, if you did subscript E and not subscript E bar, it would not give a different result. It just wouldn't make sense.
Yes.
It would not compile.
Okay.
yes,
That's the whole,
it's
I think he's just saying that once like you write the inner flag, sorry, like the inner model, like the flag is completely determined by it directly, right? Because you just take the part of it on the labels.
Yes.
the type. Yes,
Yeah.
the type of the
Yeah.
flag. If I say sigma flag,
Essentially, like writing.
it should span sigma.
So like subscript is not necessary.
Yeah, the subscript is not necessary because the part inside already contains the type.
Yeah.
The subscript is necessary to differentiate which operator you're talking about, but okay. You know, the operator that has sigma, the operator that has E has some domain, and the operator that has
Okay,
R
actually,
has another domain. That's the only reason.
a different question then that might make the subscript necessary again. Can I average only over type 1 and get something that depends on
Yes, actually, the averaging operator is slightly more general than this. You can go from some type to a smaller type, but I'm not going to be using that. And
Yeah, but this justifies the subscript, so it should be.
yeah, well, but in general, you put another thing in the subscript that says which part are you restricting to as well. But when you're restricting to the 0 part, you don't put the extra thing.
Are you averaging only single flags or also over linear combinations and things like that?
Oh, so this is a linear map. So this means that if I give you a linear combination, it's just the same linear combination of the values on each of the flags. Now, it is important that this is not an algebra homomorphism as well. So it's linear, but it doesn't preserve products at all, right? There's no reason why this preserves products, or the one of the algebra for that matter. What?
That's averaging.
Yes.
That's
Yes. Okay, is everyone clear about the averaging operator? Okay, and then we talked about these sigma extensions. So this is the definition of sigma extension, but before we actually look at that, let's remember what was the intuition.
Sorry, just to totally clarify. When you apply the averaging operator to any sigma flag, you get a positive coefficient.
Well, if it's a flag, yes.
Yeah,
If it's a flag, it's always
Positive, because
always
it exists in the type forces it to exist
Yes.
once.
yeah, it's at least one, right? And in fact, you know even what is the lower bound, right?
Yeah.
Because it's something, some falling factor, 1 over some falling factorial,
Yes.
right? Yes.
if that's if you're applying to a single element, not a linear combination.
Yes, to a single flag.
Yeah.
But a linear combination can give
A
you.
linear combination can give you 0, can give you negative things. Well, here's a trivial linear combination that gives you 0. Apply it to 0. Yeah. Okay. So any more questions regarding averaging operator or comments or? Okay, so let's go to sigma extension. So the intuition of the sigma extension was, if I give you some model, right, and say that it has some copy of sigma, you could uniformly at random label a copy of sigma, and that will give you a sigma flag, right? Remember, a sigma flag is a partially labeled model that has the labeled part is sigma, right? So from a model, if I uniformly random a copy of sigma, I get a sigma flag. If I had a large model, I would get the same thing with a large sigma flag, but random, right? A random large sigma flag. And we saw that, you know, these large models or limits of models are being coded by these homomorphisms. So if the homomorphism has positive amount of sigma, I should be able to label uniformly at random a copy of sigma and get a limit, a random limit of sigma flags. That's what the sigma extensions are going to be. You give me a limit and somehow being called labeling uniformly at random a copy of sigma and getting a limit of sigma flags. So it's a random element of the homomorphisms from the sigma flag algebra. And there's a condition. This condition is sort of what you expect from the finite, but we'll see how they come into play. So it's saying something like, if you compute the expected value of the value of this random thing in some flag, it can be what?
Expected over.
Oh, this is a random limit, right? So the expectation is over the randomness of this.
Phi is a random variable, yeah.
Well, phi no, but phi sigma is. Phi sigma is a random variable. And the condition is that computing the expected value should be something related to this averaging operator. What the intuition behind this is that this equality is what happens when you swap the order of what you're picking at random. On the left-hand side, you are picking first labeling at random of sigma, and then you're trying to find a copy of f, which can also be seen as pick uniformly at random some set, and is it isomorphic to f? On the right-hand side, what you're doing is, okay, forget the labels of f for a second. Let's try to find a subset that yields the underlying model of f, and then let's see how much that subset contributes for the labeling of sigma. Right? There is some weird denominator here that accounts for the fact that this thing accounts for injections rather than subsets, but I will not get into detail why you need this denominator. It's whatever you need to make the calculations go right. We will see more this in more detail. So is it reasonably clear, at least the intuition? At this point, I don't expect you to understand any calculation or why is this definition enough, right? Because I'm just saying, well, it's any random element that does this is going to do the job, but we're going to prove that.
In some sense, you are trying to establish a law of conditional probability for this framework.
Yes, but the definition is any random element that satisfies this is going to be called a sigma extension, and we will prove that this is enough to capture the correct thing. Okay, is it everything fine? Okay.
So again, what is this phi of superscript sigma?
It's a random limit of sigma flags that is meant to encode picking uniformly at random a copy of sigma in my phi. I give you some large object phi, a limit phi, that has copies of sigma. You can label, if it has copies of sigma, you can label one copy uniformly at random. Now it is a large sigma flag that supposedly
What do you mean it has copies of sigma?
has positive density of sigma.
That's what it says. Phi of sigma is positive.
Right, remember, phi of f phi of m for a model is
sigma is now a model. Okay, so
well, sigma. Okay, types are always models. Yes.
yeah. Okay.
And
If you have a graph of positive proportion of triangles, then
you can label
3 vertices at random, you'll see a triangle with positive formula.
yes,
And it will give
and then you can ask.
random flag labeled even.
Yeah, and then you can ask if I pick 3 vertices condition on the fact that are triangle and label them, now I get a large graph with a special triangle label, right? And this is, but it's a random large flag, right? And it's meant to be encoded by this, at least intuition. We'll see why this is indeed the case, that this condition is enough to really determine this.
Okay, now I get Avi's comment about why this is a conditional way of talking about conditional probability.
Any more questions or? Okay, so to prove these things, we're going to prove a small lemma, and perhaps this is a good refresher of some of the concepts. Here's the lemma. Let's suppose that Fn is a random sigma flag.
Just a bit bigger for the movie later.
Right. Size n. And what we're going to say is that we want to study whether this converges or not. Right? So remember, convergence of a flag is you compute densities in this flag, right? So you can plug other flags here, and these guys are elements of 0, 1 to all finite sigma flags up to isomorphism, right? And what we're going to say is that if you look at the sequence, this is convergent in want to characterize the convergence of this, but now these are random sigma flags. So this is a random sequence. So we're going to talk about weak convergence. So this is weakly convergent in that if and only if for every f there exists the limit of the expected values, right? So first, if it is weakly convergent, these things will converge, right? They're just the expected values. But what's important is that the backwards implication also holds. And in fact, furthermore, the weak limit is uniquely determined by these limits, and is supported on plus. That's the small lemma that we want to prove.
When you said P of bracket dash, this is not an F, this is an arbitrary.
Oh, yeah, this is a, okay. I can write it like this. So if I plug F in there, yeah, that's the, okay. If I plug any F in there, right? So this is an element of this because I can plug F in. Okay. Does everyone understand this statement of the lemma? Okay. So here's the proof. Okay. Here. So if we look at this space, right, this is a cube with countably many coordinates, right? If it's a cube with countably many coordinates, then distributions and weak convergence in general is completely determined by convergence of mixed moments, right? So it's enough to check that the moments of these distributions are convergent, right?
So if in the case where it's countable and not if it's infinitely countable, do you take which topology do you take on the cube?
Oh, it's product topology. It's the, well, remember okay, it's not written, but the definition of convergence requires that every time I plug some F, this is convergent, right? So every coordinate needs to be convergent. It doesn't matter how fast they are converging. So this is precisely product topology. Okay. Okay. And you know, once you put the product topology, weak convergence coming from that product topology is precisely determined by mixed moments. Okay, any more questions before we start the proof? Okay, so let's look at the mixed moment. So how does a mixed moment look like? It looks like this. N. So it looks like this, and I'm interested in
What's the tilde for?
what?
Well, tilde just to name it different.
Yeah, it's just to not be the same. So I'm interested in computing this limit, right? So here it's a mixed moment because there could be repetitions here. So if you want higher powers, you just repeat some F's if you want F tildes, right? Now, if you remember, there was a way of turning these products into joint densities, right? We did the k = 2, but there's a formula for the general case, and you can write this as Pf1 tilde E tilde F. So if you remember, here, what is going on is that you're picking these flags uniformly at random in a fixed target flag, right, and take their product. So the same thing, you can think of this as you're picking independently, right, and they could collide or not collide. And here, this experiment is saying actually you pick these T flags and they are required to not collide. So it's slightly different, right? But these two values, as the size of Fn goes to infinity, they get closer together. It's 1 over size of F, as long as you
What is the non-collision? What do you mean by collision?
Collision means, well, there's this large flag and there's a part of sigma. And what's the experiment on the left? You're going to sample a bunch of completions here, and you're going to ask whether they are isomorphic to each of the flags, right? But you're sampling them independently, right? On the right side, you do the same thing, but there's a condition. The condition is that the sets that you sample, the intersection is precisely the sigma part. So you avoid collisions,
I see.
right? But you can see that if the size of Fn is very large, as long as these Fi tildes are fixed, these two values get closer and closer together. 1 over size of F apart. You can prove that, which is somewhere there. So these two limits are the same. Now, the advantage of these is that these guys satisfy what is called the chain rule. You can compute them in steps, and then expected value is linear, and limit is also linear. So this can be written as sum of F and F sigma M for some M of here. If you don't remember what this chain rule said, was essentially saying that you can compute these things in 2 steps. Right? You can first sample something inside F and then sample of a fixed size called M that is between the 2 things. And then you can sample inside there these T flags, right? But now you're done, right? Because these limits are appearing here, right? So these limits of the expected values of densities of any single flag are completely determining the mixed moments, right? So that is the proof of the first part. Let me perhaps give an idea of the proof of the second part. People think it's too mysterious, and I will actually do it. So this actually proves the first part and actually most of the second part, because we proved that if these limits exist, then this is weakly convergent, right? Because the moments are determined. But we also proved that in this space, the mixed moments also uniquely determine the distribution. And because these guys are just the limits of the mixed moments are just being computed from these limits of expected values, this is also uniquely determining the limit. The only thing that is missing is to show that whatever this weak limit is actually supported on these limits of sigma flags, right? Now, what were these limits of sigma flags? We needed to check essentially 3 things. So we needed to check linear relations, which amounted to saying, kernel of phi contains that kappa sigma, which was giving the chain rule. We need to check that product is preserved, right? So essentially, you need to check that EF1 tilde times F2 tilde is equal to phi of F tilde phi of F2 tilde. And we need to check the 1 of the algebra. Make sure phi of 1 is equal to 1. Okay, that's the 3 things that we need to check. Just check that this is a homomorphism from this flag algebra, right? Now, linear relations, if you remember, this comes from chain rule, right? So this is always satisfied in the finite. right? So it's certainly going to be satisfied in the infinite, right? When you know, whatever these random variables are in the finite, they always satisfy the linear relations anyway. So you just take the weak limit, they will still be satisfied, right? The one of the algebra is the same thing, right? If you add all flags of a certain size and you compute the density of the sum is always going to be 1. So the one of the algebra is also preserved. The only thing that's a little bit shaky is the product. But again, the product is not satisfied in the finite, but it's almost satisfied in the finite. You know that it
up to 1 over Fn.
1 over Fn. So what you actually have to do is you have to say, well, look at the set where the product for two flags fails by more than epsilon. That is an open set and blah, 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 blah. And they use the weak limit to say, well, for any given epsilon, the probability that you're going to fail by more than epsilon in the limit needs to be 0, because if you take the limit in the finite, it's going to be 0. And then take the union, and then the product cannot fail in the limit.
But this has to use the assumption you made on the.
No, I'm not talking about extensions at all.
Oh, yeah, sorry.
I'm just the only thing that you really use is that P of F1, F2 in F minus P of F1 in F, P of F2 in F. That is less or equal to 1 over all of. That's the only thing that you know.
So what part of this whole thing will not work if you just define P of F1, F2, F to be equal to P of F1, F times P of F2, F?
When you're setting up the algebra, it's not going to be an algebra. If you try to define the product by just saying, okay, the product of F1 and F2 is just take the, well, okay. You could say, you know, define this quantity Pf1, F2 to be just this thing times F, right? This product times F. It doesn't become an algebra, essentially. You don't get the chain rule, and it doesn't become an algebra. That's what fails. You need to see what goes wrong, and you can try to fix it, and you're going to see that something else breaks when you try to fix it. And so you really need to define it this way. Okay. So is this clear? Okay. So this finishes the lemma, right? So I'm hand waving the last part, but hopefully everyone understands. Okay. So so now let's do the extensions thing then. So let's see. I'm going to erase the lemma, but hopefully the statement is simple enough that people will remember. So here's the theorem of sigma extensions, which is just saying that sigma extensions are what we think they are. So under the same conditions, so we're going to say phi of sigma is greater than 0. And let's think that if we have a sequence of models that is converging to phi, and let's say that theta n is a uniformly at random embedding of sigma and n. The theorem is going to say two things. It's going to say that sigma extensions are unique. Two, if you look, so again, remember sigma extensions, they are meant to be encoding, picking uniformly at random a copy of sigma and phi and labeling it so that it becomes a large sigma flag. So what we're going to do is we're going to say, take these models that are converging to phi and do that operation on them. And we're going to claim that this actually converges to my sigma extension. And of course, these are random variables. So the convergence here is weak convergence. Okay, so that's the theorem. Okay, so here's the proof. And I'm going to wave my hands a little bit again. So we're interested in this kind of
just define unique. I mean, these are random.
Oh, unique here means distribution unique, right? So if you give me choose sigma extension, these are two random variables. Okay, they can be different, but their distributions are the same. And that's what we mean by unique. Yeah, thank you. Okay, so what we want to do is we want to use the lemma that I just erased, which was saying all you have to do is check that the expected values of the densities in these random flags, right? So these are now random flags because the labeling here is random, right? And all I have to do is to check that those are actually converging, right? So what happens if I do expected value of P of some F in this random flag? And here's the part where I'm going to wave my hands because I'm not going to do this computation. And I'm going to say it's exactly the right-hand side of that, but done in the finite. So you get P of brackets F sigma in P of this sigma in. Now, let me just check some nonsense that I wrote in the board. P of this doesn't make too much of a sense because this is not a model. This is a number times a model. What I mean is, the number comes out. The same thing on here. Another thing that doesn't make too much sense is that I'm picking uniformly at random an embedding of sigma in n. Why is it that such a thing exists? Well, n converts to phi. Phi has positive density of sigma. So, okay, eventually there will be copies. So this will make sense, which also proves that the denominator eventually is non-zero. So everything here makes sense. And this is a computation that you need to do to check that indeed you get this, right? As long as n is, larger than f, I guess, and large enough so that the denominator is not zero, right? Which implies that if I take the limit as n goes to infinity, if we look at the right-hand side, it's just some number times some densities in these models. But these models are converging to phi. So whatever that is, this is converging, right? So this shows that these things are converging. And the previous lemma says that this is weakly converging to some random element of this hom plus of a sigma. Okay. Now, why is it that so the other thing is that the lemma also said the limit is uniquely determined by this, right? And also you can check that this, when you take the limit of this expression, you get this expression for phi sigma, whatever the limit is, right? That also proves item 1, because then sigma extensions are unique because they are exactly what happens when you take this limit, right? And these give you the mixed moments in the limit, right? Okay.
So you've proved the theorem, but you didn't motivate sigma extensions at all. It was supposed to be towards a generalization, rough generalization of Mantel or the use of.
Yes. So the idea is that we're going to use these averaging operators, and the averaging operators. Remember, the idea when we're doing the Mentos theorem was to say, you pick some vertex uniformly at random, do some computation on the flag algebra of the vertices, and that computation is non-negative, and then somehow you go back to the previous flag algebra. And so picking this vertex uniformly at random is corresponding to these sigma extensions. Okay, but it's going to come in the next lemma, which is the whole point of the Mentos theorem, which unfortunately I already raised, which is that the averaging operator preserves non-negativity. Right, which is what we wanted, right? So here's the lemma. If you apply the averaging operator to a non-negative element, so remember these non-negative elements, this is also a non-negative element, but now on the algebra that does not have any types. Okay, so here's the proof, and I think I can squeeze the proof here because it's not very hard. So what do we need to prove? Well, let's take some element in the semantic cone of f sigma, and let's take some phi, that's a limit, but without labels. And we need to prove that phi in the brackets of f, in the averaging operator of f, is non-negative, right? Okay, so case 1, phi of sigma is 0. What happens if phi does not have any copy of sigma? Well, if I try to compute phi of f, right, whatever this is, F is a combination of sigma flags, right, with some coefficients. So everything that appears on F has copies of sigma, but sigma doesn't really appear on phi. So this is zero trivially. Right? Actually, I can't squeeze the proof here, so I'm going to go here and to try to keep these things on the board for now. I'm sorry.
In a central place.
Yes. So case 2, which is the hard case, but it's still easy. Phi of sigma is greater than 0. Okay, if phi of sigma is greater than 0, well, we can consider these sigma extensions here, right? So let's consider one of them, which is the unique one, I guess. And let's compute the expected, well, there's nothing much to compute here other than the expected value of this extension calculated on F. And by the definition of extension, this is just this. Well, I'm cheating a little bit because the definition of extensions says that this holds when I plug in a flag, not a combination of flags. But you know, any combination of flags is a linear combination of flags. And you can see that this expression here, it's linear in whatever I plug in here. So the condition is only for flags, but it also applies for a combination of flags.
The denominator is constant for.
Yeah, the denominator here is constant, and whatever, if I plug small f here, it is linear here, right? So it also holds for combinations of flags. Okay, but now I'm sort of done, right? Because F is a non-negative element of the sigma flag algebra, and phi sigma is a random homomorphism of the sigma flag algebra. So whatever this number is, it's a random number, but it's a non-negative random number. You take expected value of this is greater or equal to 0. The denominator here is positive, so you know, can pass to the other side, and then you get that is greater or equal to 0, right? So that's the full proof. Any questions about this proof? Okay, so now we are in shape to do our Mentos theorem, right? Because the Mentos theorem, what was doing was, well, I guess average rate, so I don't know if I have quite here. What we did is we took some element and we added a positive element, but this positive element was of the following form. You had some type, you took some square, that is certainly non-negative on the sigma flag algebra, but then you did brackets, it's still non-negative because of this lemma. And then you were lucky enough that the coefficients are arranged in a nice way. So this is actually the whole point of the semi-definite method, which is here. So this is the statement of the semi-definite method. Is a little bit traumatic in terms of notation, so let's go it slowly. So the idea of the semi-definite method is that you are interested in some extremal combinatorics problem. What is an extremal combinatorics problem for us is some polynomial function of the densities. A polynomial function of the densities is just an element of the algebra, right? Because anytime you have a product, you can re-express it as linear combinations of densities. And you're interested in, say, maximizing this polynomial function over all possible limits. So you're interested in this phi f, which is the maximum of phi f over all limits, right? Okay, if you wanted minimum, just take minus, right? And what the semi-definite method is going to do is it's given some parameters, is going to produce a positive, a semi-definite program whose solutions provide upper bounds for this. So they deal with the hard bound for this, right? Because if you want a lower bound,
is it clear that you have a maximum?
What?
Is it clear that you have a maximum?
The space is compact. So, okay, so I guess the cube is compact, but if you remember, this is defined by linear relations and product relations, so it is also compact. It's a closed subspace of a. So you always have a maximum in the limit. In the finite, it's not, well, in the finite, you have a maximum because it's finite, but in the limit, you also have a maximum here. If you put extra constraints, then maybe the set is not necessarily closed, and then maybe it's not. You don't have a maximum, but if you're just computing overall.
If you have any open constraint, then
yes.
you ruin it.
Yes, yes. But you can still do other things. If the underlying set is relatively open inside here you can do something else. Okay. So the semi-definite method is about doing the hard bound of this. So what is it going to do is, given some parameters, it's going to produce semi-definite program whose values are upper bounds for our problem, right? So the parameters, there's a bunch of parameters and there's countably infinitely many choices for them. So here are the parameters. You pick t types and you can choose how many you're gonna pick as long as finitely many. For each of the types, you pick a flag of that type. You're also gonna pick numbers Li for each of these t types, and you're gonna pick a number n. And n needs to be large enough so that some condition holds here, which is just so that the densities that we'll eventually compute make sense. So n needs to be large enough because of this, and n also needs to be large enough so that you can express f as a linear combination of models of size n, right? So if you're trying to maximize triangle, you cannot take n equals 2 because you cannot even express triangle with 2 vertices. So these are the choices of parameters, and P is this semi-definite program. You minimize some m, and m is the maximum of a bunch of coefficients, and these coefficients are given by this computation. Now, don't look at the computation for now. I'm going to explain where it comes from. But the variables here are these capital X's that are positive semi-definite matrices that are indexed. Each xi is indexed by flags, sigma I flags of size Li. So you have a block diagonal matrix, if you want, that is required to be PST. Okay. So what the theorem says is that whatever this program is, the optimal value of that is an upper bound for the extreme combinatoric problem that we care about. And second, if you remember, when we did Mento's theorem, we could also extract some information about the extremal case, right? So that's what this item 2 is going to say is, if you give me some solution and you give me a limit that matches the solution, in particular, the solution needs to be optimal and the limit needs to be extremal. That's the only way they're going to match. Every time I have slackness in one of these constraints, the corresponding model of the constraint needs to have 0 density in my extremal phi. And every time you give me an eigenvector of the matrix xi that is not of the 0 eigenvalue, then either the sigma I type has 0 density, or the sigma I extension computed essentially on the eigenvector needs to be 0 almost everywhere. Remember, this is a random variable. So when I say almost everywhere, it means probability 1. Okay, so that's the theorem. Okay.
I expect this was fast for most people.
Yes, so now I'll pause for a second, and if anyone...
First, you want to say this, this minimization problem is a dual to the maximization problem you wrote before, and it follows all the duality theorems of convex programming. It just happens to be because we are, because of the positivity conditions on the algebra that they translate to the positive semi-definite condition on the variables that on the matrix variables that are in the program.
Right, but I wouldn't exactly say dual because there's not anything like positive Stellansatz here saying that anything that's non-negative necessarily is written as a sum of squares. Yeah, there's nothing of this kind.
There is no, so there can be a gap between the minimum here and the maximum.
Not that there can be a gap, but there can be a, you might be able to prove that a certain expression is larger or equal than minus epsilon for any epsilon. But any finite thing cannot actually see that is greater or equal than 0.
But that's okay. There are versions. There are many positive Stellansatz results, and some of them have this.
Yes, it will be of this kind.
It's the same kind. Yeah. So it's the same kind. Just the positivity that. Yeah.
And let me point out that the reason why it will be of this kind is for trivial reasons. Even if you don't take any type and just let n start growing, you're gonna see better and better values, because essentially what you're seeing is what kinds of you're essentially doing a maximization over level n. And if you cannot beat something at level n and n is growing, then you eventually see better and better values that will approach the actual maximum. So, but the cool thing is that if you, for several problems that were stuck in the literature, people did this, and this you can even program. You can put it in a computer and say, okay, use this type, this type, this type, this type, and it spits out an answer, and it turns out it's tight for a bunch of problems that were open. Okay. Any more questions? Or can I give an idea of the proof? If you're trying to understand this, don't try to understand this. The proof will become clear, and don't try to do, I'm not going to do the calculation. I'm just going to say, it's the calculation when you do this, okay? Don't try to understand by staring at this. It's going to be a little bit traumatic. Once I write the proof, you understand where this comes from, okay? So just get this is the more important part of the theorem. This is a calculation that I will say what is the calculation that gives this.
And these are these conditions, 1 and 2 are sort of the generalization of the complementary slackness.
Yes.
People have seen
Yes.
in the case of linear programming logic.
Yes.
And that's, I guess, it's also important for the external combinatorics.
Yes. Yes.
You find out which gadgets, which flags you use that were essential.
Yes.
Not with,
Can you just explain what are these positive semi-definite matrices?
Oh, positive semi-definite means it's a
No, not what is positive. What are these matrices? Why do I care about their eigenvectors and eigenvalues?
Oh, we'll see in the proof how they come up. But you know the definition of positive semi-definite matrix, or do you need?
Yeah.
Okay. Okay. So shall I proceed to put the proof? Okay. So here's the proof. So because these matrices, so let's fix some solution, right? Because these matrices are positive semi-definite, I can write them as exterior products, right? So let's write them as exterior products. Each of these VIJs are vectors, okay? So I can write them like that. Now you might be complaining that maybe I forgot the eigenvalue. I'm not assuming these are normalized. So I just made them swallow the eigenvalue. Later, it might be convenient that V actually appears in some way here, but let's not care about that for now. And let's try to mimic what we did for Manto's theorem. So we're going to take F, and we're going to say, I need to upper bound that. So I'm going to do F plus some non-negative element. And the non-negative element that I'm going to pick is this element here. I'm going to take the sum of I from 1 to t. I'm going to do the brackets of, I guess let's sum over j outside as well. Brackets of I, sum, well, let's call it sigma I, d, I, j, f squared. The brackets. Okay. So let's double check that this is a non-negative element. This is a flag times a square, so it's non-negative in the sigma I flag algebra. When I apply the brackets operator by the lemma that we just proved, that's somewhere here, this is still the non-negative element, and I'm just summing them up, right? So I can do this, right? And
what is inside the square?
You remember you wrote this as an exterior product of these vectors. So you just take the vector ij and you take the corresponding linear combination of flags. Okay? This is a vector Vij.
What's Vij subscript f? That's a vector Vij at the f?
Yes, exactly. It's a vector indexed by flags of size li. Sigma I flags of size li. So I just look at this number.
In the case of Mantel's theorem, we had only one flag, t was equal to 1, right?
So we had two flags, but only one type.
One type, right? Two flags with one type. With,
yes.
Yeah. Anyway, yeah, we had this. Yeah, so maybe it corresponds.
So in the Mantel's case, we did this. We did this minus this squared. There was actually a 1/2 as well. So I guess 1 over square root of 2 times this technically. That's what we did on the Mantel's case. That was whatever is here inside. And Fi here was trivial, was nothing. Fi was.
So in this case, we have two kinds of f's. Like the two pictures are two kinds of f's, and
Well, the vector here.
Is the vector?
The vector is 1 square root of 2 minus 1 square root of 2. This is the vector indexed by, you know, this is this coordinate and this is this coordinate. Okay.
Thanks.
So then, try to not erase that. So now I'm going to say that if you look at this, right, it's, so again, this is f plus some non-negative element, so it's certainly greater or equal than f in the semantic cone language. So, and the conditions on n is large enough so that everything that appears here can be expressed as a linear combination of models of size n. And when you do this linear combination of models of size n, so m, n, what you're going to get is exactly that whole garbage that is written on the theorem. So xm, this whole expression, is what you get when you open up this nonsense as a linear combination of models of size n. So the CMs are coming from f, and then you have these weird sums. This Q sigma i's are coming from the averaging operator, and this triple joint density is coming from Fi and two Fs that you're picking in this square. Right? So then, and then the positive semi-definite matrix is coming from the fact that, you know, you decompose into these exterior products. Okay, so you get that, but then by definition of our semi-definite program, this is at most m sum over all models of size n, but sum of all models of size n is the one of the algebra. So this is exactly m, right? So that proves item 1.
Wait, where did this little m came from?
That is the condition. Right?
Ah, okay.
Right, that's the condition. M is the maximum coefficient you see there. Right? Okay. So then you get exactly that. Right? So that proves item 1, right? Because we just showed that f as an element of the algebra is less or equal than m, right? So any limit phi of f is less or equal than the number m, right? Okay, so is this clear? Because then I can perhaps erase this, because we're not actually going to use this computation anywhere else. So let's do number 2. So, okay, so we have this phi, and we have this optimal solution and this phi that matches the value of the optimal solution, right? And remember, how did we extract some information about this extremo phi? We looked at what happened with equality, right? Because if I have an extremo phi and I apply to this proof of inequalities, I'm going to get phi f, which is equal to m, and in the end, you also get m. So this means that these two inequalities that I wrote here are actually equalities when I apply phi, right? So what happens with equality for 2? Well, what I get is that if I sum over m in mn of m minus xm minus phi of m, remember phi is linear, so it comes in, this is equal to 0, right? That's the difference between these two things. Phi applied to that needs to be equal to 0, right? But both of these things are greater or equal than 0, right? So the only way that this is going to be 0 is if every term of the sum is actually 0. So whenever this has slackness, this guy needs to be 0, right? So that gives you item A. Right? Now, what happens with equality for 1? Okay, equality for 1, there's a small technicality here, which is, remember we wrote it as an exterior product. Let's assume that V appears in this decomposition. Okay, there's a small technicality, which is this Vij's had swallowed the eigenvalues, but it's okay because the conclusion here doesn't depend on whether I multiply V by any number, by any scalar. That is how, you know, it's important that it's not in the kernel, because if it's in the kernel, the eigenvalue would turn it into 0. You cannot do that. So without laws of generality, you can assume that one of these Vij's is actually equal to V. And then when you look at equality for 1, you know, it's equality if any of these, it needs to be equality with any of these summons, right? Because all the summons are non-negative, but they need to hold with equality, so it needs to be equal to 0. So in particular, if I look at the one that's corresponding to my V, it needs to be 0, right? So equality for 1 gives me that phi of brackets fi sum f sigma I of my V f times f squared sigma I is 0.
It should be evaluated on the sigma extension of phi, no?
Well, no, it's just the brackets, right?
Oh, you did the, yeah, right, okay, good, yeah.
And then the next step is, well, if not this, right? So I'm saying either phi of sigma I is 0 or something else. If phi of sigma I is not 0, then I can take the extension, right? So this is 0, then this is going, I can take the extension and I can compute the expected value. And what you're going to get is that phi sigma of this, the same expression, is 0. And at this point we are done because this is a random variable that is non-negative. So the only way that the expected value is 0 is if the random variable is itself 0 almost everywhere. And then you can, of course, you can throw away the square, right? So this implies that phi sigma. I'm just going to write implies item 2. Okay. Any questions about this? So remember, in Mento's theorem, we use this to.
Why did you need the fact that it's an eigenvector?
Because it appears on the exterior product, right? So it's whatever is being taken the square, right?
Yeah.
Because whatever was the squares, they are non-zero. So.
In Mento's theorem, we used it for.
Yes. So in Mento's theorem, from this we could conclude that using that particular solution, we could conclude that this guy had density 0, right? And on the second part, we concluded that this guy was equal to this guy for almost every vertex, right? That's what we did on Mento's theorem, right? Okay. So any questions at this point? So this actually finishes what I had to say about the synthetic limits. So maybe let's take a break, and when we reconvene, I'm going to talk about the semantic part.
Just to maybe summarizing this, there is a semi-definite program that you need quite a bit of ingenuity for in order to pick these flags.
Yeah.
And this ingenuity has come into lots of external combinatorial proofs before flag algebra.
Yes.
Limits existed. They actually mimic them. They just, let you automate, some of these searches where the calculation is complicated, and sometimes it was important discovering.
Yes.
So that's, I think, that's the power.
Yes. This summarizes a lot of arguments that had already appeared in the literature. It's just doing this. They are doing this.
There are two advantages. One is this computational power that can, solve, in some cases, the guesses you have that you cannot verify. The other thing is that you get in many combinatorial papers in external graph theory and whatever external combinatorics, in order to even calculate when you could. What you needed to keep track of the errors because you are working with finite objects.
Yes.
This theory releases you from, because you can talk about the limit, these error terms you can ignore. And that's the other, I guess that's a more conceptual advantage.
Yes, exactly.
The thing you just said is exactly what makes you actually getting algebra and homomorphisms of algebras at the limit, right? Because you have many of these things fail, as we discussed earlier, when you add those phis which are not exactly homomorphisms at each step, but only at the limit.
No, but that's in the
Yes,
proof.
yes, so-
That's
yes,
in
but-
the proof of this,
but I-
the theorem that everything is legitimate.
Yeah,
No,
but the point is that if you wanted to do these proofs in the finite, you could without doing these algebras, but you would have to carry these epsilons
In
around.
fact, that's, yeah, you're right. That's exactly what was done. I'm sorry, I take it back. Yeah, so that's exactly.
So
what-
anytime you did products,
To account for it.
anytime you did products or squares for that matter, you would have like this hanging term saying, oh, plus some error term that accounts for collisions, right? In the limit, this doesn't happen,
And
right?
in some cases, there will be several such floating, epsilons, and you need to control the relationships, etc.
Yes.
It somehow frees you from.
Now, I should say two things. First, this really only applies to the dense case. If you're doing the sparse case, the limit becomes trivial, so this doesn't work. Now, there are ways of adjusting this theory to work in some cases, some sparse cases, but they are mostly ad hoc. And the other thing that I should say is that all we discussed is about the semi-definite method. There are at least two other parts of flag algebras, and arguably one of the most curious ones is the differential method, where you produce these differential operators in the limit, and they don't make sense at all in the finite. They come from the finite in a certain way, but they really only make sense in the limit. So you are essentially there. What you're doing is that you're saying whatever this home plus is, if you look at it as a subset of this cube, it is an algebraic variety there. And if it's an algebraic variety, you can consider the tangent space to a point, and you can move it in a direction and talk about local optimality. But that is a completely different method, but it's very impressive, and really only makes sense in the infinite. But I will not be covering this today. But it's a very interesting part of the theory as well.
What's the most complicated flag that you know that leads to a sharp bound for?
Oh, the amount of results that
was found, using.
No, the amount of results that were found using this.
So one example, just one example.
So there people have computed, for example, if you look at the theory of directed graphs and say that you're trying to, well, I guess it's not the theory of directed graphs. I think it's the theory of tournaments or something. People have looked at trying to, I think, minimize things that look like this, which is very complicated. People have looked at minimum number of monotone sequences of size k in a permutation. So even like there's a conjecture called Meyer's conjecture there, which says that this should be 1 over k minus 1 to k minus the density at least. So density, minimum density. In a permutation. Here's in a permutation. So there's a conjecture that says this, and this is a very hard conjecture. I think it's close for. So it's close for 3, that was the original paper. 4 already uses a method like this, and I think the authors say 5 can be done, 6 can be done, and 7 is already out of reach. We have
Confirming the conjecture.
Confirming the conjecture. There's also in the original paper also said something like if you forbid one of the sequences, right? Say forbid decreasing sequence of size k and minimize the other one, you get exactly this. But if you're trying to do both of them at the same time, it's not clear yet. There's some other partial results related to this. There's some results regarding like I think you minimize the number of triangles, but you bound the independent set size. And you can get some results which even the paper becomes completely unreadable because the paper says, we're going to use the semi-definite method of flag algebras. We plug in these numbers, we get these numbers. If you want to check the matrix, look at the appendix, and here's a 50 by 50 matrix that supposedly is PSD. And when you do the computations, you get the correct bound. Which, at that point, you probably trust the authors because you're not going to do them by hand.
Independent set size seems like something which is hard to.
Oh, no. Here I'm saying you bound the independent set size. You say the maximum independent set size is at most 5.
So you
And
just
what is the
use,
minimum number of triangles that you can put, right? If you're trying to compute something about the independent set size, you have to be very careful because it's not continuous in this thing. It's very easy to construct a sequence of graphs. So instead of thinking of independent set size, let's think of cliques. It's very easy to compute a sequence of construct a sequence of graphs that is converging to the full graph. So edge density is going to 1, but the largest clique is not sized linear, right? That's very easy to construct. So you need to be careful with these things. So let's perhaps take a break, and then when we come back, we will talk about semantic limits. And I'll stick around if anyone has questions.
Those examples, the flags that you plug into the SDP seem very simple.
Oh, no. These were handpicked. These were handpicked to be very simple.
But if you increase the size, if you pick many of them, they disturb your program and just becomes larger, but you still find the same.
You want to be able to say a computer to finish it in finite time.
Yes.
In your lifetime.
Yes, typically
I can take, say, one labeled vertices, so all possible combinations with one labeled versus here, right? And try to compute. Then could I find this solution or not? In the Mentos theorem.
Oh, in the Mentos theorem, yes. In the Mentos theorem, you can take
large problem, right?
Yeah, it's a very short problem. I did it by hand. So sigma has.
If I didn't know that I need to pick this.
So you would start with very small ones. You would start with very small ones.
Many small ones, and I can still solve and get solutions.
Yes.
Right?
Well, typically you would say something. How would you program this? You would say, well, you need to input the n, which is going to be the size of finite expansion, and you need to input which types you're going to use, right? And then, or you could say, maybe you just input the size of the types and the size of the flags, and then the program enumerates all possible types, all possible flags, right? This is more expensive, of course, but that's kind of like, oh, this is the full power of the thing, right? And that Mentos theorem, you can certainly do that. You can certainly do this, even if you don't know the proof. You could.
But there are places where you really need to get to large sizes of types.
Yes. Well, large sizes of types, yes, but n tends to be also a big deal as well. The finite expansion size n.
Yeah.
And this is problematic because even for graphs, when you start getting n equals 8 or 9, it starts becoming huge because remember that at some point, you have a matrix that's indexed by all graphs of size n up to isomorphism. Like n equals 9, this is already starting to become large. And it's even worse than that because when you're doing flags, you partially label the graph and you need to consider all possible things up to isomorphism of that, which is even larger. Sure. So
I just don't like, but there are examples where the flags have more than like 4 or 5 verses.
Yeah, so first I can give you an example of one that I did, which is tournaments. We ended up using, I don't remember exactly which, I think it was the tournament that the paper has more than one tournament, but one particular tournament was this tournament here, where you put 5 vertices like this, and it looks like a cycle. Right here, it doesn't matter what it's them. And so any guy here beats that. So, and then you're trying to, I won't say maximize, and to maximize this. And the kinds of flags that we used, I think we used these kinds of flags. We used this type, and we added, I think, 1 or 2 vertices to this, and ended up appearing. So all possible flags of this type of size 5.
I see. So this, like, if you just enumerate, not enumerate, if you just try everything up to this size.
Yes, and in this problem, you can also check that if you're going to do by semi-definite method, you need to go at least to this for extremality conditions, because the extremal configuration of this looks like you take a C3, and then inside each part, you take a C3 and so on. It's a recursive blowup of C trees. That's the extreme.
And like, just out of curiosity to get the intuition, is this the only flag you use?
No, you use also this flag appears at some point. You use this flag, and I don't remember if you use another one.
Okay.
But the way that we did was actually the way that he said that you just put all flags first, see that you get the bound, and then you start trying to trim. Because the point of trimming is that the semi-definite theorem, when you have way too many types, they kind of contribute at the same time to do the solution, and you cannot extract too much extremality information. So if you have fewer types, it's better. If you have
So M needs to be much larger.
No, sometimes you just do the solution with many types and you see that some types are superfluous. If you throw them out, the program finds another solution. What?
Maybe, I don't know if everybody, but maybe we can continue the discussion. We will have some material, yeah.
Oh,
But you all said it would be like it.
but is it clear or?
Yeah, no, I just wanted to get a feel for that.
Okay. All right. So now we're going to talk about semantic limits. I guess I already erased the triangle picture, but what is different between a semantic limit and a synthetic limit, or semantic limit, also called geometric limit, and a synthetic limit, also algebraic limit? Notice that we really were doing algebraic manipulations over all these, right? And the limit object is not really an object, it's a list of numbers satisfying some relations, right? Semantic limits are going to go in the opposite direction. So what is the opposite direction? Well, the direction of flat algebras was the minimalist direction. You try to encode the minimum amount of information necessary. Whereas semantic limit, we're not going to care about that. We're going to actually try to keep the geometry of the object inside of the limit. And we would really like that densities in this limit were actually just computed as some normalized count of the copies that you see in the limit. So in particular, it needs to be well defined what are copies in the limit. And this was complete nonsense in flat algebra homomorphism, right? I give you a list of numbers and I say, what's a copy of a triangle in this? You have no idea, it's a list of numbers, right? So to start, let me give you some, let's start with very simple cases that appeared before. We're going to start with the theory of graphons and then go to the theory of hypergraphons. This is going to give a good intuition, and some of the notation and etc. will actually be reused when we go to general limits. So let's start with graphons. And the advantage of semantic limits is that you can give a definition. You don't need to go through all the turbo, define an algebra and etc. It's very easy to give a definition of a graphon. It's just a function.
Sorry, so you should say this is intended to be an infinite graph.
Yes, I was going to say exactly that. So it's a function that is symmetric, measurable, that goes from the square to the integral. And this is meant to encode limits of graphs. And the way that you want to think of this is that it looks like an adjacency matrix, right? So if you think that the vertex set is the interval 0, 1, if this was either 0 or 1, it would just be an adjacency matrix because it's symmetric. Okay, there's some condition of measurability that will come in later, but there's something weird, which is maybe it has fractional edges, right? But that is fine, right? So you
can think of them as probability.
Yes, exactly. I was going to say the intuition is that Wxy is meant to be the probability. That X and Y are adjacent. Okay. So that's the intuition of a graphon. Now, if you have this in mind, it's very easy to compute or guess what would be the formula for the density of a finite graph in this. And this is something that's going to happen for semantic limits in general. It's more convenient to work with label densities. So label densities here. So this here I'm already preemptive. The setup for semantic limits is going to be the same. We're going to work with these universal theories. So these are this is the label density. And it's going to be the number of embeddings of m divided by the maximum possible number that you would see, which is this falling factorial. So in graphs, you're just asking, well, how many labeled copies do you have of a graph inside the other? And if I give you a graphon, and you wanted to compute what was this in the graphon for a graph in the graphon, and you wanted to guess a formula, you would probably guess a formula that looks like this. So if I give you a graph G, and you want to compute the density on a graphon, well, you take one variable for each of the vertices of the graph, one variable in the interval, and you require that the xi's are mapped to edges, but remember, edges are given by these probabilities. So every time I give you an edge of the graph, you want to see an edge in the graphon. And of course, every time I give you a non-edge, I can write it as an edge of the complement. I want to see a non-edge in the graphon, which is just a complementary event. This is integrated over all these x's, right? We could just, you would probably guess this formula if you were trying to guess this. And of course, just so that we are everyone in the same page, there's no loss of generality of considering these label densities because there's a convergent formula. And it's true in general, not only for graphs. You can just use the symmetries of M to convert between labeled and unlabeled densities. Previous P that we were considering, there is this conversion. So even if you wanted to compute P on my graphon, you could just use that formula to compute P, right? Now, the main theorem of graphons, Lovász and Szegedy, from before, is that graphons, and I'm going to write like this informally, they correspond to limits, right? So limits of graphs, not for any theory, of course. And by corresponds means, you know, every time I give you some convergent sequence, there's a graphon that actually captures the limit, right? Now, it's important that this correspondence is not one-to-one. And this is the content of what is called the uniqueness theorem, but we're not going to cover the uniqueness theorem. Okay. So already notice the difference, right? Because for flat algebras, it was a list of numbers, but here we already have something that really looks like a graph. We can talk about vertices in this thing, right? We can talk about edges. It's just that it's a little bit weird because edges are kind of fractional, right? But if you wanted to talk about, say, a triangle in the graphon, you could also talk about a triangle in the graphon. It's just going to be 3 points such that, you know, there's positive probability that there will be edges, right? So this is already feels very different from a syntactic limit, right? Is it clear? Everything?
Are you going to say something about sampling or not?
About what?
Sampling.
Not really at this
point. Okay, so let me say one sentence.
Okay.
This graphons can be thought as a model of random graph with some properties. If you want a graph of a finite size n, that looks like W, what would you do? You would just pick n points, x1, x2, xn, and for each xi, xj, W will tell you what's the probability that an x will be there. You will cross this point, and so you will see a random graph that has the same structure in the limit as n grows, like W. In fact, this sequence of graphs as n grows will converge, obviously,
Yes.
to W. So it's really a way to describe, random graph models. And the simplest one, the Erdős-Renyi one, would be, I'm sure you all know, would be just a constant function W, which is 1/2 everywhere.
Yeah, that would be the Erdős-Renyi 1/2. If you exact Renyi P, it's just constant P.
Maybe we should add that the labeled density of like any graph in W is exactly the expected label density of.
Yeah, is the.
Yeah, that's right. Yeah, and that sort of comes in the proof, but of course.
Okay, so now we're going to talk about semantic limits in general, right? And in general, things are not so nice because you have more variables. And so if we're going to do general limits, in particular, we need to do the case of k-hypergraphs. And so you could ask the question, what is a k-hypergraphon? And you could try to figure out the answer by saying, well, a graph is nothing more than a two hypergraph, right? So you could say, well, let's just take that definition, see every time that a two appeared there, and let's plug a k, right? So is it true that a k hypergraphon is just a function from 0, 1 to k to 0, 1 that is, symmetric and measurable? Is that correct? Does anyone have intuition of whether this is correct or incorrect? Anyone that preferably does not already know the answer? So it turns out that this is actually not correct. And the issue, there is a classical example that shows what's the issue with this representation, which is like this. If we think about graphs, as Avi mentioned, if you take the random model GMP, this converges with probability 1 to the constant P graph. So WP, where WP is constant P. Okay. Now, that is very nice. This is graphs, but we could consider a 3 hypergraph obtained like this. You let H and P be the triangles of GMP. So take the same vertex set, and every time you see a triangle on your sample of GNP, you put a hyperedge there. It's not hard to show that H and P, because GNP is convergent, H and P is convergent. Because if you want to compute densities of 3 hypergraph here, you can re-express them in terms of densities of graphs, right? Because you know how it's being computed, right? How these guys being constructed from a graph, right? But okay, so to actually prove that no such thing can represent this limit is complicated, but let's just do an easy case, which is the following. Because GNP looks like a constant, well, the intuition why it looks like a constant is that every vertex here looks the same. That is morally an intuition that you could have in your mind, and it wouldn't be completely incorrect. And here, all vertices are also going to look the same because it's just triangles of the previous case. So a very natural guess would be to say, well, maybe it's the constant function as well, equal to, whatever is the edge density there, which should be P cubed, right? But that's not going to work. And the reason is, if you consider this hypergraph here, so this is K4 minus, and it's the hypergraph that you have all but one of the 3 hyperedges on 4 vertices. You have all these edges, and you don't have this edge is missing. So K4 minus. This guy, if it was a constant function and you do the same definition here, you're going to see that this guy has some induced copy, right? Has a copy inside a constant function. But it certainly does not have a copy here, because once you have all the white edges, it forces triangles on all these, and then it forces all edges in the underlying graph, and then the red thing is also a hyperedge, right? So this is a very big problem for this kind of definition, right? And you know, it's more complicated, but you can check that no function like this will actually be the limit of this. And the problem is that if you look at the definition of graphs or graphons, what happened there is that you have some vertices, and then you have WXY is giving you some level of randomness, some randomness at the level of pairs. And for hypergraphs, you're trying to do the same thing, but you only have randomness at the level of the K tuple, right? So every time you have something that's going to deal with interactions with pairs, or something that is coming from something that really should be randomness at the level of pairs, this is not going to be able to encode it. So the correct way of doing this is actually more complicated. So what we're going to do is we're going to say, let me, given a set of vertices V, let's denote RV as the set of finite non-empty subsets of V. Forget the finite for now. It will come in later, but non-empty subsets of V, let's think of that for now. And then we define EV to be 0, 1 to RV. So we're going to put way more coordinates than just K. We're going to be interested in actual EK, but we're going to use this notation later. So I'm defining it now. So EK is this guy.
EK is the new graph.
Yes, so well, not exactly. So this is the definition, and for us, a K hypergraphon is
out of K, you mean out of brackets K?
Yeah, brackets K.
Yeah.
This is an abuse of notation that I will be using all the time.
Okay, no.
Yes, brackets K. So a K hypergraphon is a symmetric measurable subset of this space. Okay, so that is the definition. So it's very different from graphs. We will see why is this actually encoding a limit of hypergraphs, but nevertheless, at this point, I want you to observe that there's way more coordinates, right? Even if I take K equals 3, you already have 7 coordinates, right? So you have 1 for each vertex, 1 for each pair, and 1 for the triple, right? So there's way more coordinates here, and you have essentially a level of, if you're talking about K hypergraphs, you have variables that are encoding randomness in each of the levels up to K, okay? So if I'm going to have any chance of saying that this is encoding the limit, I need to tell you how do you compute densities in this thing, right? And in the spirit of semantics, we want to say densities should be nothing else than some count of the number of copies, right? So what I actually need to tell you is what is a copy of a finite K hypergraph in this thing. Now, to do this, we're going to reveal what is a copy of hypergraph in another hypergraph, because I want to rewrite it in a way that stands nicely over there. So, okay, so what is a copy? And by copy here, I always mean labeled copy of some hypergraph G and some hypergraph H. So everything in the finite, right? So what is this? Well, I can think of this as being a tuple, right? XV and X by vertices of G, and this tuple is a tuple of vertices of H. So this is here, such that, well, every time I see an edge of G, it needs to be the case that X alpha 1 up to alpha K, up to X of alpha K is an edge H, and for every alpha that is not an edge, so this is the complement, you also need to see a non-edge. That's the definition of a copy of a graph, of a hypergraph in another hypergraph, right? Now, if you look at these things, what is going on here is that you're looking at a particular set of coordinates of this big tuple, right? So there's some projection going on here. What is the kind of projection that is going on here? Well, every time I consider some tuple, right? So this is a tuple of vertices of G, right? Let's think that this is injective, because for our case, it will be, because I'm trying to encode edges. This defines some projection very naturally in the other way from tuples of vertices, VG length tuples of vertices of H to K tuples of vertices of H. And the definition, the natural contravariant definition here is that if you want to compute some vertex, so this is an element here, so this is an element here, so I can try to compute the value of this at some vertex V, and the definition is that is just the corresponding coordinate, right? So what is going on in this expression here is that this guy is nothing more than alpha star of X, right? And the other guy as well, right? So I'm saying that it's a tuple of vertices such that for every edge, alpha star of X is an edge of H, and for every non-edge, alpha star of X is a non-edge of H, right? This means that if I want to talk about the set of copies, so set of copies, this is going to be the end of G in H. Well, it's going to be set of tuples, and I can write them as preimages based, an intersection of preimages based off of these projections, right? So I can write them like this, alpha in EG, alpha star -1 of EH, intersection, alpha in EG bar, alpha star -1. Okay. Is everyone fine with this definition of the set of copies? And of course, if you want the density, then it's all right. So it's just the size of the set divided by the following factorial. Okay. So now we're going to do essentially the same thing, but for hypergraphons. And the idea is that this symmetric measurable subset of EK is the edges of my hypergraphon. And the vertex set is 0, 1. It's always going to be 0, 1 for us, but the symmetric measurable subset of EK are the edges. But so the difference here is that now a limit K tuple is this weird element of EK that actually has way more than just K coordinates. It has, 2 to the K minus 1 coordinates, right? So we're going to do the same definition. So the set of, or if H is a K hypergraphon, then G is still a hypergraph. We're going to define the set of copies of G in H to be the same intersection, except, so let me just write intersection. So instead of doing EH, I'm going to put the hypergraphon here, and instead of doing EH bar, I'm going to put the complement of that here. Now, of course, this doesn't make any sense with this definition of alpha star, but we're going to do a different definition for us, which is the one that makes sense. So again, if I have a function that goes from K to V of G, no. Oh, it's V. Yeah. This defines now a natural function. So here you had a function from K to VG, and it went to VG length tuples of vertices of H to K length tuples of vertices of H. Now we're going to do the same, but with limit tuples. So you're going to take a VG length limit tuple and map it to a K length tuple, but limit tuple. And the definition is the natural one, which is this guy is going to be an element of EK, so it has coordinates for subsets. So if I want to compute a certain coordinate A, I'm just going to do X of alpha of A. So this function goes from K to V. I can compute it in subsets of K, right? And that is the corresponding function, right? So this is the set of copies, is the same analogous definition. Okay, is it clear?
You want to, you really want to take count of all the, you start with a K level, with a K uniform hypergraph maybe, but you want to look at all the K minus 1, K minus 2 different hypergraphs that are defined by it, in a sense, right? So for every hyperedge, K hyperedge, you want to maintain some consistency of its, of the complex beneath it.
Yes, sort of. Yes, sort of. Not exactly, because you're not considering these variables that are corresponding to lower levels. They somehow are capturing a different kind of randomness. So it's not necessarily. It's not really correct to think of it as it's like a downward closed thing.
No, it's not the downward closed. I mean, your example of your counter example to the original definition, to the wrong definition of graphons. So it's not, shows it's not a downward closed.
Yes.
And that's the reason it doesn't work to capture it just by this.
Yes.
Numbers at the case level.
Mm-hmm.
But you are, you need information about the K minus 1, K minus 2.
Yes.
Yeah, sort of implied. There are not other hypergraphs. They are just defined pair, subsets of vertices.
Yes, but if I give you a hypergraph, it's not really clear what is this information that is hidden a priori, because
it's not clear. I mean, you cannot. I mean.
If I give you a hypergraph, a finite hypergraph, it's not clear what is this hidden information. This hidden information really only appears when you take the limit.
Also, in continuation to Avi's note from earlier, let's say you do have some specific hypergraphon. Do you have any corresponding way to sample from it?
Yes, there is.
So what exactly is that? Maybe
so the sampling that you do from that is, well, it's somehow suggested in here, but what you do is, if you want to sample a model, a graph of size n, you're going to sample a random variable in the interval 0, 1 for each of the subsets of brackets n, right? And then you're going to look at these projections that are given by tuples and look at all subset, take any subset of size k and look at all coordinates corresponding to subsets of that. Is that, when you look at these coordinates, now it's a limit k tuple. Is that in the hypergraphon or not? If it is, you're going to put an edge. If it's not, you're going to put a non-edge. That gives you a way of sampling a hypergraph of size n from this hypergraphon. And
can you repeat it? I don't think I followed.
Okay, so maybe I'll write it. You sample. So if you want to sample,
even sampling from the constant hypergraphon, which is it will not be constant, right?
Well, yeah, I'll tell what is these things later, but
this is not compact. Like this is going to be a problem.
What do you mean compact? Compact with respect to which topology? That's
the topology that's. I mean, the constant one is kind of like this is kind of like only a 0, 1 function, right? So but that has density 1.
You do not know what is the topology, and you do not know how these are encoding graphs. So you're anticipating what I will talk in a second. But okay.
So you delayed on purpose talking about the topology even for graphs.
Yes.
Okay.
Yes. Well, here, if you're expecting something like cut norm, it's not going to happen here.
Yeah, in cut norm, this is not going to be compact.
Yes, but cut norm here is not really the correct thing to do.
Okay, but there is a norm where you don't need to take the compactification. Okay, I'm just like.
Then the topology here is
just.
So first, let me just finish this definition, which is what you're going to say is that if you want to compute densities, is just the measure of the set of copies, right? So if you want the topology, you can just say, okay, this gives me the densities, and that puts any guy here in that cube, right? And then that gives you a topology.
Okay, and this is actually compact.
That is compact, but for silly reasons, right?
Yeah.
Now, of course, there are collisions. There are collisions in the same way as graphons. 2 points are being mapped to the same thing, but they represent the same limit, so you don't care. But to go back to the sampling, if you want to sample K hypergraph of size n, what you're going to do is you're going to sample X in En uniformly at random. So remember, En here, you have one coordinate for each subset of brackets n, and then you're going to say that alpha is an edge. So let's call this hypergraph G of size n. So we're going to say that alpha is going to be an edge of G if and only if alpha star of X is in the hypergraph. So in other words, what you're doing is you want to check whether a certain K tuple of vertices is an edge or not of the thing that you're sampling, right? Take this set of K elements, look at all subsets of that. There are the coordinates corresponding to these subsets. Look at those coordinates. Now, this is a perfectly valid element of EK, right? Check whether this perfectly valid element of EK is in the hypergraphon or not. If it is an edge. If it's not, it is not an edge. That's how you sample. Right? And this is going to converge the hypergraph. That's the theorem.
But the fact that you're in this topology basically says that you lost the geometry. In a sense, not really. But
well, you didn't lose the geometry because it still computes complex.
Take a topology which is more like the cut norm and then take the completion.
Yeah, well, I think this is still, last time I checked, it was still an open problem to find something similar to cut norm that actually gave you exactly the same topology. You can define the cut norm and it has some uses here, but if I remember correctly, the cut norm defines a finer topology than what you want. But you can, there's a construction of the limit via this stronger cut norm that you kind of juggle it around and you say, okay, it gives me more than I want, but if you do tricks in a certain way, it works. But it's kind of, it's not as natural as in the graphons that it gives you exactly the same topology. This doesn't happen here. There are reasons.
How this generalizes graphons?
What, sorry?
Can you explain how you get graphons this way? Because it looks different.
Yes, I was going, this was the next topic. I'm going to say, well, how do you get, why a Chu hypergraphon is certainly not a graphon. This is obvious, right? Because a Chu hypergraphon is a subset and a graphon is not a subset. So what is the correspondence? So correspondence is this. So if you have, so here's graphons, hypergraphons. So it's not going to be one-to-one. Again, there is no way to make it one-to-one either. So if I give you a graphon, the corresponding hypergraphon is the set of points such that x1, 2, so the variable of the pair is less than the value of w computed on the graph of the graphon. Not really. It's a this guy is the integral of that. Yeah, integrating the top variable, and that is the other way around. If I give you a hypergraphon and you want the graphon, you do xy, wxy is the measure of z's such that xyz is in the hypergraphon. Here I'm abusing a little bit notation, and What I mean by this is that this guy is indexed by 1, this guy is indexed by 2, and this guy is indexed by 1, 2.
In what sense do you still have geometry?
Oh, you still have geometry because you can talk about copies, you can talk about vertices, right? That's why you have geometry here. And we will see how this is going to be important. I will do it after I do the definition of the more general object. We will see how I'll prove a small application where you see that if you try to do it syntactically, it's not clear how the proof goes. There is a syntactic proof of the theorem that I'm going to do, but it's completely different, right? So geometry is there. So the other comment I wanted to say here, so it's clear that it's not one-to-one, right? Because if you go around, it's obvious that you don't land on the same place. Well, I guess if you start here, you land on the same place, but if you start here, you don't. And it cannot be made one-to-one. So for example, GNP, right, the random limit graphon, there's only one that represents it, except for zero measure change. Over here, there's way more than one, even if you account for zero measure changes, because anything that, you know, the top variable has measured exactly P will represent it, right? And you can shift it around. You can even make the P part be in different places. So
you can assume probably someone here, you can definitely assume monotonicity, but maybe always.
What do you mean monotonicity?
The set is monotone with respect to, you know.
Yeah, for hypergraphons,
but
yes.
maybe
you could, without loss generality, you could say hypergraphon is a set like this, such that the top variable is always the bottom part of the interval, right? In here, it is fine to do this. And in fact, in general, you can do something similar, but it doesn't help you much. It doesn't help you much doing that. It's really more correct to think of them as subsets. It's easier to manipulate. So are these things clear? So these are how we compute these densities and then these copies. Okay. So the next step then is to do the general case. In the general case, surprisingly, we're almost done with the definition of the general case. There's a technical thing that I need to say first, which is actually any universal theory. And in fact, here is the technical thing. I'm not going to do it for universal theories. I'm going to do just something that we call canonical theories. Canonical theories, what they are is that I have a further requirement that every predicate is injective. Formulas, you can say the theory proves that for every x, if there are some coordinates that are equal, then the predicate is false in the tuple. Now, this is, you might think that I'm losing something. I'm actually not losing anything. You can prove that there's a very nice notion of isomorphism between theories, and you can prove that any universal theory is isomorphic to something that is like this. And let me give you a very silly example that will probably convince you that this can be done. Think of not necessarily simple graphs, right? This is not a canonical theory because the edge can hold on XX. But how do you encode this as a canonical theory? Take the theory of simple graphs and add a unary predicate that's going to say, is there a loop in this vertex? Right? And it's very easy to see that, you know, if you know how to compute densities on this, simple graphs with an extra unary predicate, they correspond to densities of not necessarily simple graphs once you know, move things around. So we're going to use canonical theories for technical reasons. There's some complications that arise if you don't do this step, but you can do this step without laws of generality. So now we want to define the general case, right? And the general case, there's an analogy with the way that you define models, right? And how do we define models? We start by saying, well, each predicate symbol, we want to have a relation, right? What was a relation? It's a set of k tuples where k is the arity of the predicates, right? So we're going to do the same kind of thing and say, what is a limit of a predicate, of a single predicate? That is what we call peon. For a predicate P, we call it a peon. And it's going to be a set of limit k tuples, right? But we know what are limit k tuples, right? Limit k tuples are elements of this guy, right? So peon is a measurable. Again, we need measurable because at some point we're going to take measure subset of. So KP, remember, is the array of the predicate, right? So it's a set of limit tuples of the appropriate array, right? Now, if we think about models, the next step after you define relations is to define structures, right? So for us, we're going to define the analogous version of that. It's called an Euclidean structure. This is a function n that maps to a peon. Okay, so that's what is an Euclidean structure, right? You just, in the same way that a structure was a collection of relations, one for each predicate, an Euclidean structure is a collection of peons for each predicate, right? Which are the limit relations, right? Everything clear so far? Now, the next step is to talk about models of the theory, or theons, which will be our case. So we want to somehow say that a limit of my theory is going to be an Euclidean structure that satisfies the axiom. But now that is a little bit complicated because I don't really know how to compute whether a formula is true or not in this thing. So we're going to go a roundabout way. And remember that canonical theories, or actually universal theories, right? A silly way of checking whether something is a model or not is to say every substructure is a model, right? Anything that I look inside it is a model, right? For a universal theory. This is kind of silly in the finite because, you know, you can just look at the whole thing. But even if you look at the infinite, right? If you would take an infinite structure, it's enough to check that for a universal theory is enough to check that any finite thing is a model, right? So we're going to cheat in that way because we're going to define a theon based off of that. We're going to say that a theon is an Euclidean structure such that if M is an L structure that is not a model, E, yes.
M is a.
Yeah, finite.
Yes, finite.
Oh, yeah. Then M does not appear so as long as I can compute so this is not a definition yet because I didn't say what this mean does not appear, but as long as I can do something similar to hypergraphons where I can say, oh, here's the set of copies, I could try to say, well, if I give you some structure and the set of, it's not a model, I'm going to require, it doesn't appear, right? So we're going to do the same thing. And I'm going to perhaps try to take advantage of this formula. So what we're going to do is we're going to say N is an Euclidean structure. And what we're going to do is we want to compute the copies of a certain structure M in N. And it's going to be the same intersection, except that I'm going to do over all predicates. So E is becoming P here. G also M, I guess. This is going to be the corresponding peon. This is going to be the corresponding relation. And this is EKP. And again, this allows you to compute densities in a similar fashion as well. by just saying it's the measure. I can do it. So here is the same kind of definition of projections, except that now because predicates are potentially having different arities, they define different projections based off of the arity. Right? So that's the definition of the set of copies of a certain structure, finite structure M, inside my Euclidean structure, right? And now if you want, I guess you're left, but you can sample structures of a certain size in a similar manner if you want, with something similar to this. So, okay. Okay, so now we have a way of computing copies, so I can complete this definition, but notice that there are two options here. So option
The definition, what is the model of the theorem?
Oh, we know what the model of the theorem.
The models are infinite structures, so you would like every.
No. So model here, model just means finite structure, and you want to take a finite structure, whether it's a model or not. Right? And if it's not a model, I'm going to require it to not appear in my Euclidean structure. Okay, that makes sense. So for example, I don't know if you're doing for graphs, a structure is anything that has a binary predicate, but it could be that the binary predicate is not symmetric. And yeah, it could be that it's not symmetric. And then if it's not symmetric, then you're going to require to not appear in the 2 hypergraphon, right, in that case, but more generally in the theorem. Now, requiring it to not appear, there are 2 options. Option 1 is you remember that actually we really only care about these densities, right? The copies are very convenient, but we really only care about the density. So we could require just that they don't appear in this sense, right? The density is 0, right? And option 2 is that they actually don't appear. So the set is, well, you would like to say empty, but for technical reasons, you cannot say empty. You have to say this, where this is what's called the diagonal set. So here. So you can either say the density is 0, so maybe it appears but only in a 0 measure set, or it doesn't actually appear. And for technical reasons, what it means to not appear is that maybe it appears on the diagonal. There's some vertex variables that collide. That is a place where you really cannot control, and somewhat related to why you need to use canonical theories, because messy stuff happens here and you really can't control it. But this set is of measure 0, so it sort of doesn't matter anyways. So the difference between these 2 guys is the difference between what we call a weak theon and a strong theon. So if you require 1, we call it a weak theon. If you require 2, is a strong theon. Okay? Is this clear, the definition? So the big theorem of the theory is perhaps what you'd expect by this point. Is that, well, first, big theons. These correspond to limits of the theory T. That's the first theorem. Again, this is not one-to-one.
There's not T on the right-hand side. It's the homomorphism unit. There's no T.
Yes, I'm abusing a little bit. So this is the first theorem, and the second theorem is the same theorem with strong, but actually you can say it's slightly better. So this is what we call the induced Euclidean lemma. Which is this: if n is a weak theon, then there exists a strong theon n prime such that they differ on a zero measure set. So why is it called induced Euclidean removal lemma? Is because, well, I give you something that potentially has copies, but only a zero measure copy, and then you can completely eliminate them by just changing a zero measure. Now, there's another connection that I'm not really mentioning here, which is via ultra products, and you can actually take this and prove a removal lemma in the finite based off of this. So that's also another motivation for this, but I will not do this today. Okay, so these are the two big theorems. Okay, there's another theorem that I'm just write something here, but I'm not going to state, which is called the uniqueness theorem. A uniqueness theorem, so I'm not going to state the theorem. What it actually says is it characterizes when two limits represent the same limit. It represent the same limit of like, but it's more complicated, and I'm not going to get into details because it's quite technical, even to state. Okay. So, any questions about this?
These theorems are in your work.
Yes, this is.
But in particular, if you take an element of on plus, you can go.
Yes.
You can go to a strong theon.
Yes.
And then if you go back, it will take you to the same one.
Yes. Well, this direction is fine because uniqueness here is trivial. Right?
Sure.
If you give me two elements of on plus, they are the limit of the same.
So what I'm saying, you could think of on plus as strong theons.
Yes, you can think of strong theons. Okay. Any questions so far? Okay. So I don't know if I'm going to have. Actually, I'm out of time.
There's a theorem that can be proven.
Yes, I was going to give an idea of proof that is of geometric proof, but
of what statement?
Yes.
So at least we should see the statement that has different proofs in the semantic and the syntactic worlds. Maybe you will not do the proof.
Yeah, I'm not going to do it again all the time.
Just the statement.
But here's an example, a theorem that an application that I was going to give a very neat proof in the semantic, which is a theorem from quasi-randomness, and it combines graph quasi-randomness with tournament quasi-randomness. So I'm going to put some names here. Some 9 and 91. And I'm also going to put some quotation marks because if you go to these papers, you're not going to find this theorem. You actually need to take these results and think about it for a second, and then you can get this theorem. So it's not actually there, it's a consequence of what is proved there. So what the theorem says is this. So G, let's assume that G is 1/2 plus random, so it's a graph. Or if you want, is a sequence of graph converging to the constant 1/2 graphon. And let's assume that these are, since I'm not going to prove, I'm just going to say, are linear orders. G, H is given by, so H is another graph, and it's going to have the same vertex set. But what you're going to do is that you're going to flip every edge in which the orders disagree. Conclusion is that H is 1/2 plus 0. This might look trivial at first glance because you might be thinking, okay, I take two orders and then I sample a graph uniformly at random, and whatever, if you flip whatever the orders disagree, it's going to be 1/2 quasi random. Yeah, but the order is different. I give you the sample of the graph, and then you give me the orders. The orders can look at the randomness of the graph to be decided. So it's adversarial. The choice of the orders is adversarial, and still you cannot disrupt the randomness. That's what this theorem is saying. Okay. So let me just restate this in theon language, and perhaps I can just give a couple of words of why it's easy to see the proof in the infinite with semantic limits. For theons, what you're doing is you're considering the theory of graphs and the theory of linear orders, two linear orders. And you have some theon in, and you know that NE is 1/2 quasi random. And what you want to show is that NE n+1 2 is also 1/2 quasi random. And by our translation, we know that what 1/2 quasi random means. 1/2 quasi random means that if you take the measure of these sets, is 1/2 almost everywhere, where the set is the section. So this is how you state it in the limit. And the way that you can prove this semantically, I'll just say a couple of words, is you can prove that if you have a strong limit of linear orders, then it actually cannot depend on the variable that's indexed by the pairs, except for a zero measure set. In a strong linear order, it cannot depend on the top variable except for a zero measure set. And then when you do the symmetric difference, well, you only care about what happens to the top order. So when you take the symmetric difference, it doesn't look at the top variable. So it's just going to flip a set that has measure 1/2. It's still going to have measure 1/2. And so that's how a semantic proof goes. But I don't have time to do that. But the original proof, if you go to these papers and try to see how the proof goes, is actually a syntactic proof, and it's much longer. It even has the problem that is done in the finite, so there will be epsilons and deltas flying around.
It's not that difficult. I mean, it's basically that if you take an adjacency matrix and you take some matrix of it and flip the zeros and ones, you would the second eigenvalue, if it was,
Oh, but it cannot be any matrix.
No. It's good. This matrix had to begin with little n eigenvalue.
No, but the matrix you're flipping, it cannot be any matrix that you're flipping, right? The matrix needs to come from.
Sorry, no.
If you flip any matrix, then you can get any graph.
Of course, very good. Okay.
This is not trivial at all.
Okay, very good. Okay, great. Yeah, excellent. Okay, thanks.